This is our introduction into heat. You should already be able to define heat and energy and define endo and exothermic reactions, but by the end of the video, you should also be able to determine how heat and work affect the system and surroundings in an E equals Q plus W. We'll get to it. Use Q equals MC delta T from the regions chemistry to determine the heated change in the system. And after you get that, convert those joules to kilojoules per mole for a reaction. So first, we just need to define a few terms. System includes anything that we're studying. So the molecules are here, hydrogen and oxygen, and the surroundings are anything else. So here might be the cylinder and the piston. If you feel the outside, it might be your hands in the air that it might be exposed to. There's multiple types of systems. An open system allows for energy and mass to change, like an open cup of coffee or a beaker. So the open system is just like you boiling water on a saucepan. A closed system allows for changes in energy only, like a closed coffee cup or beaker, or a closed saucepan. Literally, the name closed system makes kind of sense, where the energy can change but the mass cannot. The third type is an isolated system. An isolated system doesn't allow a change in temperature or heat to occur, like a perfect calorimeter. So it needs three examples. You have an open test tube, which would be an open system, a closed test tube, which would be a closed system, a closed test tube in an isolated area would be an isolated system. We want to make sure that when we were doing our heat labs that we're using isolated systems, so not only closed, but also allowing no heat to transfer. We're only looking at what's happening inside the system. So there are a few changes that we can go through and determine the changes in energy into the system. We've been talking since last year about heat, and if the heat's going into the system, the Q, or heat, would be a positive endothermic reaction, and if the heat was coming out of the system, it was called Q minus, or heat was coming out exothermic. But now we're also going to talk about work. Work is how much the energy in the system is doing, so how the system might be expanding or contracting, the particles might be moving around to change the pressure of the system. And together, the heat and the work will tell you how much energy is going in or out of the system. So again, the first, the W is talking about work. And the ability of a system to do work or transfer heat is all the energy. Energy is both work and heat. So the first law of thermodynamics is energy may be transferred, but not created or destroyed, or conservation of energy. So I can either do work or transfer heat, and those should offset one another. You should be able to determine where all the energy went and where it came from. So again, with the heat, we said there's two types. There's endothermic reactions, which energy goes into the system, and it's probably not spontaneous, which we'll get back to, probably not spontaneous. It's a low stability positive value, and exothermic reactions in which energy comes out of the system is probably, again we'll come back to that, probably spontaneous, and has a higher stability and a negative value. So usually we consider endothermic reactions to be cold to our touch, because remember we are part of the surroundings. In the system, the heat's going into that system. It's coming out of us, so that's why we feel cold. And exothermic reactions we consider to be hot to us because we are the surroundings. To the system, it's leaving the system. So it's exothermic in regards to the system. So really important you know which one feels cold or hot to the touch. And then in going back to work, this idea is kind of similar. Work done on a system is going into the system and would be positive energy, and work done by the system, such as a gas expanding, will be a negative because the energy is exiting the system. So on or into the system is positive, by or exiting the system is negative. It's kind of like if you work out. If you work out, you're going to execute energy, that energy is going to leave your system, right? So we would say that's a negative value. However, you went to the spa and you got work done on you, like your pedicure done, your eyebrows tweezed, your hair done, that's going to give you more energy. You're going to feel more confident, right? So that's going into the system and positive. And so the general rules are written in the yellow box. I would prefer that you pause the video and make sure you write it down. Work is also defined as negative pressure times the change in volume. So again, what we were saying is compression of a gas means that we have to push the gas. And because we're doing that work on the system, we're considering that to be a positive value. But when we're talking about a gas expanding and doing its own work, we can't make a gas expand. It has to do it on its own. The gas's particles have to actually move, and so in that case, it's work done by the system and negative. So really important that you write down about compression and expanding of gases. So we can see some examples. So here's your work and heat examples. In the first question, the work done when a gas is compressed in a cylinder is 462 joules. So I'm pushing by 462 joules on the right column. Maybe I'm putting even more weight on the right side. the heat change equals 128 joules from the gas to the surroundings. So since it's going from gas to surroundings, we have to decide if both of these values are positive or negative to determine our total change in energy. So again, according to those rules in the previous slide, if you're compressing in a cylinder, we're putting in 462 joules. And if the heat changes 128 from the gas surrounding, the gas is losing 128, so we would say it's negative. So I'd say negative 128 and positive 462, and we'd net them together. Again, it doesn't matter what order you write them in as long as they have the right charge. So the negative 128 because it's going away from the system, and the positive 462 because it was going in, we're compressing it. That means overall the system is still obtaining 334 joules even though it was releasing the heat that we can feel. There's internal work being done. Here's another example. A gas expands and works on the surroundings equal to 279 joules. It absorbs 216 joules. Calculate the change in energy. So this time again, we have to determine what charges we want. If the gas is expanding, it's doing the work. The work is negative 279, and it's absorbing 216 joules. That means it's going in. So even though this feels like the energy is going into the system, that's only for the heat. It's still doing work. So we have to say negative 279 plus 216 is a negative 63 joules. It's losing energy even though it's absorbing heat. So that's really important. We realize that those are two different terms. So one more time putting it together. If the heat's going into the system, it's positive. If it's losing, it's negative. If work is being done on the system, it's positive. If it's being done by the system, it's negative. And that net value, if it's positive, will be a gain of energy. And if the net value is negative, it'll be a loss of energy. Really important you understand that stuff. There are two types of energy we've been talking about for a while. Kinetic energy refers to the energy of motion. It's proportional to the temperature of the system. And the potential energy refers to stored energy within its bonds or forces or in a nuclear system. Kinetic energy we had a formula for on our reference table. It was 1/2 mv squared because we were saying the more they move, the velocity, the more energy they have. They'll move a little less if they're heavy, so the mass does play a role. Potential energy we don't particularly have a formula for on our table. The units of those energies we usually say are a joule. This is the man joule on the right side. And the joule is actually coming from a couple of different units. It's actually coming from the previous equation. If you remember, the previous equation was kinetic energy is 1/2 mv squared. So it's 1/2 mass in kilograms. And then the velocity is meters per second, but remember it was squared. So mass meters squared per second squared. Instead of writing those units over and over and over, joule just made the unit joule. Okay, so it's actually a combination of units. In other places, we might actually see calories. Calories is another way of mentioning the energy. We don't see it on the AP anymore, but I just want you to be aware that calories is also a unit, and there are 4.18 joules per calorie. So both of which are considered to be, metric, but not necessarily used as calories anymore. But we still call it calorimetry. That's where it gets its name from. Calorimetry is measuring how much energy is going into or out of the system. And since we can't measure the exact energy of the reactants and be like, hey, how much energy do you have? We have to find their delta H, or change in energy, I should say heat, through calorimetry or heat flow. Each substance has its own heat flow, and that's called specific heat, or simply C, as the amount of energy required for 1 gram to change 1 degree Kelvin or Celsius. The change in Kelvin and Celsius is the same. So every time you go up 1 Celsius, you go up 1 Kelvin. You'll see on this list, you're never memorizing really any of these, that the metals have low specific heats, and that's because they change energy very well. We call them conductors. Things that are more gaseous have higher specific heats because they're usually insulators. Water is the only one I want you to know. Water is 4.18 joules per gram Kelvin, and that one is pretty high because water does not change very easily. That's why the ocean always feels pretty cold. There's also something called heat capacity. Now, heat capacity is for a substance like the actual calorimeter or a thermometer or a piece of something that is a mixture of things. So you get specific heats for specific elements or compounds, but you get heat capacities for devices that have a mixture of those things. And that means that that device, big C, is actually equal to the mass times the specific heats of each of the individual parts. And they figured out through labs how much that calorimeter or how much that thermometer is taking out heat for you. So it's usually reported with the calorimeter or with the device, because remember that it's part of the surroundings, the thermometer and the calorimeter, so it might be pulling heat out of your system. So it's something that we use to fix our answers from last year. So one way we do calorimetry is by measuring out in a calorimeter, but sometimes we are not so efficient. The calorimeter can react sometimes, and we want to make sure that we don't burn up our calorimeter. So sometimes we do it in a disposable styrofoam cup, nested together with a top on it so it's closed and isolated because of the styrofoam. You usually want a stirrer so you can get an average temperature, not just a temperature in that corner. And you usually have a thermometer through the top so you can measure its change in temperature. And by carrying out the reaction in the calorimeter, you can measure how much heat is exchanged by the system into the surroundings, which would be the calorimeter and any water you put in there. If you don't fill it up with water, it's also going to be going to air inside that calorimeter. The specific heat of the water is 4.18 joules per gram Kelvin, and that could also be Celsius, and we measure this calculation by MC delta T. So here's an example. Put 466 grams of water into that calorimeter. Its temperature changed from 8.5 to 74.6. Maybe I added like something in there, or maybe I put it on a burner, and we want to know how much is the heat change. So we're going to use MC delta T. The mass was 466. The C is 4.18 from the previous slide, and the change in temperature is 74.6 minus 8.5. I get an answer of 130,000 joules. That could also be reported as 130 kilojoules, right? Here's another example, 869 gram sample of iron. They gave this C because you're not supposed to memorize anything but water. Cools from 84 to 5, calculate the heat change. So the mass was 869, the C was given at 0.46, and the temperature change was 5 minus 84. And so if you put that in final minus initial, you'll get the right Q charge. But it made sense because notice it was cooling, so it was relieving 32,000 joules, whereas in the first one it was heating up, so that's why we have a positive value. So the negative value when you're losing heat and feels colder to the touch, right? Hotter to the touch, but colder to the system. Negative 32,000 joules can also be reported as negative 32 kilojoules. Here's another calorimetry example from last year. We put copper into water and we saw how much it changed the temperature. So they put a 7.85 gram copper in heated to 70 degrees and placed in a calorimeter with 5 grams of water at 10 degrees Celsius. And they went to an equilibrium where they both reached 20 degrees where it stopped changing. I want to know what the specific heat of copper is. Unfortunately, I don't know enough about the copper. I don't know if you do the copper specific heat, I don't know its heat Q. So I'll start with a Q of water first. So the Q of water was 5 grams of water times 4.184, the specific heat of water, times 10 degrees. So the water only went from 10 to 20 degrees, right? This gave me a heat of 209.2. That heat of the water wouldn't have occurred unless we put the copper in. That heat directly came from the copper that was hot, right? So otherwise the water would have stayed 10 degrees the whole time. So that Q of water is also the Q of the substance, but negated because the Q of the substance was releasing its heat, right? So I just negated the 209.2, put it in for my Q of copper. Copper weighed a mass of 7.85. I'm solving for C, and the delta T was from 10 to 70, so negative, 20 to 70, so negative 50. If you drop the negatives, it wouldn't have mattered because they were going to drop out anyway. You're solving for a specific heat, which will always be positive values. I got 0.533. You can report it as joules per gram Celsius or joules per gram Kelvin, right? Because the Celsius and Kelvin change is the same. There are two more formulas from last year. The heat of vaporization. It's used when no change in temperatures occurred, so you can't use MC delta T. The HV has to be given for you, but it's the heat that it causes the vaporization from liquid to gas or gas to liquid because they're the same phase change in the opposite direction. And so the general rule is if HV is specific to the substance, like specific heat, the stronger the intermolecular force of the substance, the higher the HV will be. Right? I'm sorry, I didn't put it in there. So the higher the HV will be because that will resist phase change. An example of this question would be calculate the heat absorbed when 5 grams of water vaporizes. We're just going to say it was 2260 joules for every gram, but I have 5 grams, so I multiply the two numbers together. 11,300 joules or 11.3 kilojoules. One more type is heat of fusion. This is used again when there's no temperature change taking place, but it's going from solid to liquid or liquid to solid, so it's freezing or melting. Again, HF is specific to the substance like C. Every substance has its own. The stronger the force is, the higher its HF because it's resisting that change. And so an example would be calculate heat resorbs when 5 grams of ice is melting at 334 joules per gram. So 334 joules for every gram, but we have 5 grams. So I'm multiplying the numbers and we get 1670 joules, which would also be 1.67 kilojoules. So my question is, which took more energy, to vaporize or to fuse? Remember, the vaporized one was 11,000. The fuse was only 1,000, and the reason being HV was higher, right? It takes most substances more energy to vaporize because you have to separate the gases out much farther away than separating it out from solid to liquid, so it requires a lot more energy. So how would this be tabularized in a data table? If you look at the heat curve for a substance, notice that it anytime the temperature change occurs on the ice, water, or steam lines, that would be Q equals MC delta T. When you have the plateau of ice and water at 0 degrees, that would be MHF for fusion. And when you have the plateau at water and steam, that would be MHV because it's vaporizing there. So you would use MC delta T on the first, MHF on the second, MC delta T again to solve anything on this curve, MHV for vaporization on the plateau, and MC delta T, on the steam. And notice that again on this graph, you can see it takes longer to vaporize than it does to fuse because the HV is usually a larger number than HF. Last, enthalpy is an extensive property, meaning it depends on the sample you have, the amount of sample you have. The more sample, the more heat you'll need. Delta H for this for a reaction is a forward reaction is equal in size but opposite in sign for the reverse. So if you know the heat of a forward reaction, you just negate it for the reverse reaction. And if a reaction is doubled, multiplied by any number, the heat will also be multiplied by that number. So if you do the reaction twice, you'll need twice the amount of heat. If you triple a reaction, you'll need triple the amount of heat. It's not exactly like putting multiple things in your oven and setting it to the same temperature, because temperature and heat are not the same thing. So the amount of heat it's absorbing is twice or triple amount. If you half it, it's going to be half the amount that it's releasing or absorbing, right? Enthalpy is the fancy word of heat. Q is in the lab, heat is, enthalpy is in a published value. So if we wanted to just talk about one more example, a 1.435 gram sample of deck iron is burned in a calorimeter, and the temperature raised from 20 to 25 degrees Celsius and change. The mass of the water equals 2,000 grams, and the heat capacity of calorimeter, the calorimeter who is also absorbing your heat, is 1.8 kilojoules per every Celsius it changed. We want to know what the molar heat of combustion is. How much did we release when decking was burned? So we're going to do an MC delta T, which would be pretty normal. 2,000 grams of water, 4.18 for water's temperature change, and temperature change 5.67 overall. But notice I also added in a little bit chunk. This chunk is the 1.8 kilojoules, which in joules would be 1,800 joules. For every degree it went up, so notice I changed the degree the same. That means that not only is the water absorbing heat, but because and only because they gave the heat capacity of calorimeter, we have to consider that in our calculation. If we don't consider it, it's part of our error, right? So we add it all together, and we get 57,607 joules, which we should sig fig that, and maybe change it to kilojoules to be clear. If I wanted it kilojoules per mole, like our last bullet on our objectives, I would need to know how many moles I use. So I'm going to do the 1.435 grams of deck iron. I probably would have given you the mass of that, so 138 is how much deck iron weighs. I don't expect you to know what deck iron is. We divide and we find out how many moles it is, and if I want to know kilojoules per mole, I'll change these joules to kilojoules, which would be 57.6. And I would divide it by the moles. Notice I didn't change the number of sig figs yet. I'm doing it at the end. I get a crazy number of joules, or a normal amount of kilojoules if you change it. And this is how we change from joules to kilojoules per mole. We divide by 1,000 and then we divide by the moles. At this point, you should determine how heat and work affect the systems and surroundings using E equals Q plus W. Use Q equals MC delta T to figure out just the heat exchange for that energy, and convert that to kilojoules per mole for a reaction.